welcome back to the Sardine project. And we've been a bit remiss at recording these recaps, but today I just want to recap what we've been doing for the last month and a half and get everybody up to speed. So we've been looking at how to use the size of a gene, in particular when genes are a bit too small, that could indicate that our assemblies have a lot of small indels and introducing these mutations or false mutations, and so we can try to use that to make a estimate on the quality of the genome. So we started by trying to utilize the CheckM2 intermediate output, and that worked partially, but it wasn't as good as we hoped, and that's no fault of CheckM2. That's not why it was computing the things we were using, and so we decided to, okay, can maybe we use eggnog mapper as our reference, because so the problem is, so let's say we have a gene and the gene is 361 amino acids. Is that long? Is that short? Well, it depends on what the gene is. If you have 361 amino acids in certain orthologous groups, maybe that's long. If in others, maybe that's short. And so we were going to be using eggnog mapper, and so that's what we've been doing for a while. And there's a couple of sides to this. So one which we've done is run eggnog mapper on our simulated data. So our simulated data includes all of these mutations, and we sorry, I should be here starting to share. Oops, sorry, no, I didn't want to do that. Our simulated mutations include eggnog mapper. We had to add a little bit of engineering here to avoid computing eggnog mapper on the same sequence over and over and over again, and so instead we first collate. So we get rid of all of that redundancy, and then we run eggnog mapper, and then we expand it, meaning that we get as if we had run it on all of the redundant data, but without actually having run it on all the redundant data. So we did that. Then we used the GMGC as we had done before as a reference, and so here I'm just gonna run this until here for now, so that it's running. It's gonna take a couple of minutes. So we're using the GMGC, so the global microbial gene catalog as a reference, or the subset of the GMGC that only includes complete genes, as the reference, and we are sort of doing exactly the same thing. So if you have a gene there that's 360, that's assumed to be complete, and if that belongs to a specific orthologous group, then we can use that as a sort of as a benchmark, as a sort of to calibrate the right. And so we do this more or less what we had done before. This is more or less the same code. Before we were using KOs that we had gotten from CheckM2. Now we use the same thing from eggnog mapper, right? And then we do here, trying to do more or less the same thing, generate the plot. This is going to take a little bit of time, so I'm going to add here let's actively do it. And so we're going to do exactly the same as we had done before. So we have this background distribution, and we convert everything to z-scores, and I don't want to do everything, so we convert everything to z-scores. So this was just for now. I'm going to remove this code. We had again a little bit of engineering here. We get the orthologous group, read it, and then on stream I actually made a big mistake here, because I got confused between the sizes in nucleotides and in amino acids, and they are equivalent, except nucleotides is 3 times longer. So I think I ended up incorrectly multiplying it by 3, or when I shouldn't have. So I was comparing the size in nucleotides to the distribution in amino acid sizes, and obviously what I got was that all the genes were way too big, and then it seemed really odd. Then I sort of ran out of time, so I couldn't figure out exactly what was going on, but it does seem that there is something, there was obviously something wrong there, but once I fix that, then it actually looks quite good. And unfortunately, this takes a while to compute, so I am just going to directly show you the result, which is this one. This one. So you can see again, a little bit unfortunate that we have the legend there, not particularly informative either, but let's just see if we can get, you can see that, see, so I'm gonna actually, so if I just, here I'm just editing with Inkscape, just get rid of, so we can see here, this is what we had before. Each of the solid lines represents a genome. As we add more and more mutations, actually interesting how this is probably a specific gene, and you can see that there is still some genes, some species that seem to have shorter genes overall. Maybe we should look into that a little bit more, but if I compare to what we had gotten before, it does. So this is what we had before using the KOs. There seem to be more overlap, so the dashed lines, the horizontal dashed lines represent the original species, and so here, as you can see, here we can see that there was more overlap in this picture than in the newer one. So it does seem a little bit better. We will continue to look into this. Maybe there is something about these. Some of these species are just. So some of these species might just be a little bit weird. Maybe we can detect that. So maybe we can just improve this metric. But this is actually nicer. It looks a little bit like a cleaner version of this. Still not as clean as we would like. So what we would like is to have all of these dashed lines up there at the top. Oops, sorry, no, the dashed lines at the top, and they all start so that everything starts at the top, and then it goes down as we increase the number of mutations, because this means that we still have a lot of confusion here. So if we get, for this metric, if we get a number like -400, it could indicate that we are here in one of these curves with thousands of mutations, or it could indicate that we just have a species with short genes. So let's see tomorrow. We'll clean up a little bit more. There's some ideas we have talked about, we haven't really explored. So this is using, for example, this is using all of the OGs. We could try to figure out if maybe a few of them are better. But let's talk about that tomorrow. So everything is on GitHub, actually, especially where is it? It's on that side, especially after this recap. I'm gonna just push this fix that I did, where I've now used the correct size of genes. So again, all of these very basic things, nucleotides versus amino acids, and just this miscounting. So much of bioinformatics is just making these same silly mistakes over and over again, off by 1 errors. But such is the life of a bioinformatician. So I hope to see you again tomorrow or later today, depending on your time zone. and talk to you soon.